The scientific method is the process by which science is carried out. And this is basically how it looks like. You might find a different list if you look at a different source, but this is the general idea. Number one, as a scientist, you ask a question. And maybe your question is this particular chemical going to be beneficial in reducing someone's cholesterol, right? That could be an example of a question you might want answered if you're trying to develop cholesterol medication. Number two, you decide what your null hypothesis is and what your alternative hypothesis is. And typically, the alternative hypothesis is what we are trying to find evidence for, and the null hypothesis is the converse of that. So in my example about the cholesterol medicine, my alternative hypothesis is yes, this medicine is effective at reducing cholesterol, and the null hypothesis is no, this chemical does not reduce cholesterol, right? It's either one or the other. They're converse to each other. Number three, decide how much evidence is required to reject the null hypothesis and make a conclusion in favor of your alternative hypothesis. This is what we want to happen. And when I say you have to decide how much evidence, is like if one person takes this pill and their cholesterol goes down 1 point, is that enough evidence? No, that's really not enough evidence because it might have happened randomly. And so this is a statement about how many individuals you need in your sample size and how much change do you need to see in their cholesterol. We can combine both of those ideas in terms of probabilities later on. But you have to decide how much is required. 4, design an experiment or a study intended to gather the evidence. Step number 5, you have to publish your entire plan, right? Before you even do anything, before you collect any evidence, before you collect any data, before you take measurements, before you recruit individuals, you're going to go out there and publish your entire plan. You're going to say, listen, this is who's involved. These are the researchers working on it. This is where our funding is coming from. This is how much evidence we need to make our conclusion. This is our intended sample size. We plan to recruit 200 individuals for this. These are going to be our methods for carrying out the experiment. Is it going to be double blind? Is it going to be single blind, etc.? Here are some confounding variables that we think might affect our ability to draw a conclusion, and this is what we are doing in our experiment design to try to control for those. And you make this public. We'll talk about why in a second, but we do that before we carry out the experiment. Step number 6, you carry out the experiment. You follow the plan as closely as possible. Number 7, you do the relevant statistics calculations to calculate what's called a p-value from the evidence. Then you take your p-value that you calculated and you take your level of significance that you decided on before and you compare the two. Which one is smaller? If the p-value is smaller, then you conclude in favor of your alternative hypothesis. That's what you want to happen. And if the p-value is larger than your level of significance, then you have to conclude in favor of your null hypothesis, which means you haven't enough evidence. You don't have enough evidence to show that your drug is effective. And then number 9 is you publish your conclusion, you publish your data, you allow other peers, other scientists to review it and make sure you did your calculations correctly, make sure your experiment design was valid, and so on. That's called peer review. And importantly, you publish regardless of what results you find. Even if you find negative results and you have to conclude in favor of your null hypothesis and you don't have enough evidence, you still go ahead and publish that, even if you didn't get what you want. The null hypothesis is, like I said, it's like the baseline. It's the unassuming thing, right? Like most chemicals don't reduce people's cholesterol. So we begin by assuming that this is not going to reduce cholesterol. The alternative hypothesis is the thing that you're trying to provide evidence for, right? It's the discovery that you want to find. So these are converse to each other. The level of significance, we represent the level of significance with a lowercase Greek letter alpha. And this is the maximum probability you're willing to tolerate for incorrectly concluding in favor of the alternative hypothesis. Like I said, it's also kind of a measure of how much evidence you need to conclude in favor of your alternative hypothesis. So if you set this maximum probability too high, you're requiring less evidence, but then you're also inviting the possibility that maybe you incorrectly conclude in favor of your alternative hypothesis. And then the p-value is actually something that's calculated. That's the probability that the alternative hypothesis is false. So we want the p-value to be small. If the p-value is less than the level of significance, we reject the null and we conclude in favor of the alternative hypothesis. If the p-value is greater than the level of significance, we fail to reject the null hypothesis. That means there wasn't enough evidence. So exercise 2 says, explain why we need to decide on the level of significance before conducting the experiment. And this is the reason why. If we didn't, you could first gather data. Number 2, calculate your p-value. And then number 3, you could decide on your level of significance. And let's say the p-value we find is 0.7. If I calculate a p-value of, sorry, let me make that 0.07. That doesn't make any sense. What if it was 0.07? If I hadn't decided on my level of significance yet, and I want to conclude in favor of my alternative hypothesis so that I can publish my results and be proud of myself or whatever, then I just need this p-value to be less than the level of significance, right? So now that I get to choose my level of significance, am I going to choose a alpha of 0.05? No, that would be under 0.07. I should choose alpha equals 0.08, right? Just because that's convenient for me to conclude the conclusion I want to find. And you see why that's a problem, is like the researcher's opinion now becomes the conclusion regardless of what the data says. So instead what you do is you're supposed to decide on alpha, and maybe you choose something like 0.05 because you haven't gathered the data yet and you haven't calculated the p-value, and then you gather your data, and then you calculate your p-value, and you find that it's 0.07, well then in this situation, which is what we should do, 0.07 is greater than your level of significance, and so we conclude in favor of the null hypothesis when we publish. The whole idea is you want to be unbiased by the data before you make this decision. You need to make this decision on how much evidence is really needed before you've gone and conducted your experiments. That way you're not kind of biasing your conclusion. This is also why it's important to go ahead and publish your entire plan for your experiment before you carry out the experiment. Because if I decided on an alpha, and then I calculated this p-value, and I haven't published anything yet, and nobody in the outside world knows what my plan was, I could just take my eraser and change my alpha back to 0.1, right? Like, part of it is that you tell the entire outside world what your plan was, including what the alpha was. Now, explain why it's important to record and publish the entire plan, including the intended sample size, the level of significance, and the methodology. Well, we already talked about level of significance, but let's talk about intended sample size. Okay, suppose that what I'm trying to show is that a certain fraction is greater than a half. Let's say that's my alternative hypothesis. I want to show that this fraction is greater than a half. So I could recruit 30 individuals, and suppose I find 14 of those individuals belong to this fraction that I'm talking about, right? And so 14 out of 30, that's actually less than a half. And that makes me sad because that's not what I was intending to find, right? I wanted to show that this fraction was greater than a half. But what I could do is now let's just increase our sample size. I don't even have to throw out the old data, but let's just increase this to n equals 100. And whenever I go out and I recruit 70 more individuals and I figure out whether or not they belong to this group, suppose with these 70 new individuals, I find that x is equal to 55 and n is equal to 100. Now 55 out of 100 is greater than half. And that's what I was trying to show, so I'll publish those results. Do you see what I'm saying? So before we conduct the experiment, we tell everyone our intended sample size. And that prevents this kind of scope creep where, oh, I didn't get what I wanted, I'll just increase the sample size. Oh, I still didn't get what I wanted, I'll just continue to increase the sample size until eventually I get the result that I'm trying to find.
So you don't want to increase the sample size just to make it fit your narrative.
Exactly. Okay. Yeah. The idea is we want to eliminate possible sources of bias. We don't. Every researcher is human. Every researcher has their own opinions, but we don't want the researcher's opinion to be reflected in the conclusion. We want to have an unbiased conclusion. Okay, so that's an example of what not to do. The important thing is you publish everything ahead of time. So exercise 4 says Bob is the defendant and he's standing trial for murder. So the prosecution thinks that Bob murdered somebody. It's your job as the jury to figure out what is the null hypothesis in this case.
That Bob is guilty?
That's...
Oh, wait. If we're doing innocent till proven guilty, then the understanding is he's innocent.
Yeah. The null hypothesis is that Bob is not guilty. The alternative hypothesis is Bob is guilty. And you're exactly right to say, you know, in the United States, we assume people are innocent until proven guilty, which means the hypothesis I'm trying to find evidence for is that he's guilty. He's not going to be found guilty unless we have sufficient evidence to demonstrate that. And so we start by assuming the null hypothesis, and then only if we have enough evidence do we conclude in favor of the alternative. The level of significance here is like what probability is acceptable for sending an innocent man to prison. Right? If you think a 5% probability that you send an innocent man to prison is acceptable, then you would say alpha equals 0.05. If that's not acceptable, maybe you're only willing to accept a 1% chance that you're sending an innocent man to a prison, then maybe alpha is 0.01. But it's a double-edged sword. If I decrease alpha, we decrease the risk of sending an innocent person to prison. But also if I decrease alpha, that requires more evidence in order to put away a criminal. So
So for like a
there's
problem
trade-off.
like that, would it be up to us to figure out?
I probably wouldn't put this problem on a test.
Okay.
This is just more of a question to get your brains moving today, thinking about the concepts.
Technically, any decimal you put on there would technically be correct. It's just like opinion based.
Yeah,
Technically.
right. I want you to more be, the question is more about like, what does the level of significance mean?
Yeah.
You know, not so much what is the number. Landscapers are filing a class action lawsuit against Roundup because exposure to the product is allegedly linked to health issues down the line. What is the null hypothesis? In this case, we would start off by assuming that Roundup is safe to use. And the way our legal system works is you cannot win your lawsuit against Roundup unless you can provide sufficient evidence to show that Roundup is not safe. So our alternative hypothesis is the one that requires evidence. And in this case, we're required to find evidence to show that Roundup is not safe. Otherwise, we just assume that the product is safe. And so again, the level of significance, this is just a conceptual question, is like, what probability, what's the maximum acceptable level of probability for ruling in favor of Roundup when potentially their product might have caused some health issues? So here's some more examples. In medical safety trials, like before a product gets to the store shelves and before you get to use your Nasonex or your cholesterol medicine or whatever it is, they always try to put it through a bunch of trials, both, computer simulations and animal trials, and then eventually human trials to show that their medicine is safe before use. And the way you would structure that hypothesis test is you begin by assuming that the medicine is safe to use, and then you try really, really hard to see if you can find any evidence to show the medicine is unsafe. That might sound a little bit backwards, but if you begin by assuming the medicine is unsafe, then you can't ever find enough evidence to show that it's safe. So you got to start somewhere. We just assume that it's safe first, but we use very conservative values of alpha that make it easy to mark it as unsafe if it happens to be unsafe. Again, in the realm of like medical trials, you always begin by assuming that a drug is not effective. And then you should be able to find evidence that the drug is effective if it's effective. So that becomes our alternative hypothesis. And then in terms of like science, like physics, we always begin by assuming that the old theory can better predict the outcomes of physical experiments. And if you've developed some new theory, you are responsible for showing there's enough evidence that your new theory makes better predictions about physics or chemistry or whatever it is. You'll notice that in the courtroom, we never say the defendant is innocent, right? Like if a jury rules to let a defendant go free, they never say, we prove that the defendant is innocent. They just say, we don't have enough evidence to show that this defendant is guilty. We say the defendant is not found guilty. But not guilty is different from innocent. Okay, type 1 and type 2 errors. If, in reality, your null hypothesis is true, but you make an error by concluding in favor of your alternative hypothesis, that's called a type 1 error. Separately, if in reality your alternative hypothesis happens to be true, but you make an error by choosing the null hypothesis, that's called a type 2 error. The level of significance is the probability of making a type 1 error when the null is true. The level of confidence is the probability of making a correct conclusion when the null is true. So that makes it 1 minus alpha. That's the complement rule for probabilities. If the alternative is actually true, then we talk about beta and power. And if the alternative hypothesis is true, beta is the probability of making a type 2 error. And if the alternative is true, the power of the test is the probability of making a correct conclusion. So ideally, you want your level of confidence to be high, and you want the power of your test to be high, while you want the level of significance to be low, and you want this beta probability to be low as well. But you can't have it both ways. It turns out that there's trade-offs depending on where you set that threshold. You can't have it both ways. Okay, so in real life, we get to choose the level of significance. In situations where it's okay to make a type 1 error, like it's okay to rule for your alternative when the null is actually true, then that's the case where you choose a large value of alpha. A large value of alpha would look like 0.1. That would be considered pretty large. If it happens to be really bad to have a type 1 error, you really, really don't want to have a type 1 error, then you would choose a small value for alpha, like 0.01. If we're doing drug safety testing, we might choose an alpha of like 0.1, which is a pretty large value of alpha because it's okay to make a type 1 error. In the context of drug safety testing, a type 1 error means that you've decided your medicine is unsafe, when in reality the medicine happens to be safe. Because that's just erring on the side of caution, right? That's just like, okay, we're going to hold it back. We're going to do further testing. We're going to keep, an eye on it. In most settings, we use a level of significance 0.05, which would correspond to 95% confidence. That's typical. Especially for like fields like psychology or sociology or something like that, where it's not like super hard science, but it's also not like a matter of safety. In particle physics, they use a really, really, really small value of alpha. And the reason that particle physicists can do a really, really, really small value of alpha is because they have the time and the money to conduct a lot of experience and gather a lot of data, and that means they can be very, very, very certain about their conclusions. Okay. We're finally ready to do a hypothesis test. I have a claim. More than half of people with a New Year's resolution will give up before February. From a survey of 50 people, 27 admitted they gave up before February. Choose alpha equals 0.05 as the level of significance. So part number 1 says explicitly state the null and alternative hypotheses. If this is my claim, that means this is the alternative hypothesis. But the way I want you to write this is I want you to write P is greater than 0.5. Because P is the symbol for the population fraction. So I'm saying the fraction of the population who will give up before February is greater than half. The null hypothesis is the converse of this, which means the null hypothesis is just telling me that my alternative hypothesis is wrong. And so that means my null hypothesis is any case where the population fraction is less than or equal to 0.5. And when you look at this, there's one number where I switch from being in the realm of my alternative hypothesis to the realm of my null hypothesis, and that's called a threshold value. And we represent the threshold value with p with a little 0 subscript. And that means my threshold value this time is 0.5.
Sorry, how do you get the threshold value?
The threshold value is the number that switches from the null to the alternative hypothesis. So less than or equal to half, null, greater than half, alternative. The place where I switch from here to here is 0.5. Explicitly state the level of significance. So the level of significance is 0.05. That's given to me in my problem. Is there any evidence at all in favor of the alternative hypothesis? Yeah, because if I were to go ahead and calculate the sample fraction is a p with a hat, and that would be 27 out of 50. And that's definitely larger than half. That's 0.54. And if that's larger than half, then that means there's at least a little evidence and importantly, if this was less than half, if my sample fraction was less than half, then I don't have any evidence. I've got 0, right, to support my claim. But if it's greater than half, that's some evidence. I don't know how convincing it is, though. My claim is about the entire population, but I've only found that 27 out of 50 in my sample, fit. So that's some evidence, but it's not super convincing. Like maybe it's just 27 because of random chance. Maybe the actual fraction is less than half. It depends on the sample that I choose. So then we calculate the test statistic for this scenario. And the test statistic for us is going to be a z-score. The test statistic is going to be a z-score, and it's going to be, let's see, the number of standard deviations that my sample fraction is away from the threshold value. And my standard deviation is going to be given by the formula square root of p times 1 minus p divided by n. Hopefully that looks familiar, because the last time we met, we were talking about how this sample fraction is a distributed random variable. And even though the number of people in this sample who gave up would be a binomial random variable, we can approximate a binomial distribution with a normal distribution. And the standard deviation of the sample fraction was the square root of p times 1 minus p over n. And what p are we going to use? We're going to use the threshold value, the place where we switch from null to alternative hypothesis. That's the p0 that shows up here. That's what we're going to use to calculate the standard deviation of this. Otherwise, this is a z-score, and a z-score tells you how many standard deviations away from the mean is your random outcome. And so we divide by the standard deviation, we subtract the mean, and this time we're again assuming that the mean of our distribution is this threshold value, because we're trying to make the difference between the null and the alternative hypothesis. So that's where we're going to kind of center our probability distribution. So we're going to calculate this test statistic. And for us, that is 0.54 minus 0.5 divided by whatever I get for this number. I have to pull up Desmos really quick. And in Desmos, we say, I want the square root of p times 1 minus p divided by n, where n was 50. So my standard deviation is 0.07071. And then I can calculate the test statistic in Desmos as well. And so my test statistic is 0.5657. And again, this is a z-score, and this is what's called the test statistic. The next thing we're going to do is calculate the p-value. And we're going to be able to calculate the p-value if I take my test statistic and I plug it into a standard normal distribution. So the standard normal distribution is the normal distribution with mean 0 and standard deviation 1. And in this case, I want the probability that more than half is my fraction. And so I'm going to use the right area and try to find the probability that x is greater than or equal to my test statistic, 0.5657. So that this shaded red area under the curve is telling me what the probability is that I would get a sample with 27 or more, let's call them quitters, right? Out of a sample of 50, randomly selected if the true population fraction was a half. I'll say that one more time. If we begin by assuming that the entire population fraction is exactly half, then whenever I select 50 individuals at random to be part of my sample, there could be exactly 25, there could be 27, there could be 23, there could be 35, right? It could be anything. But the probability that 27 or more make it into my sample of 50 is going to be represented by this red shaded area right here. So this probability, this red shaded area, is my p-value that I've been trying to calculate. In other words, my p-value is 0.2858. 0.2858. But you're going to need to use the Desmos test mode app to calculate your p-value when we do these hypothesis tests. So that means, how do I interpret the p-value? Well, first of all, there is let me say, if the true population fraction is exactly 0.5, then there would be a probability of 0.2858 that I could get 27 or more quitters in my sample of 50. So if I were to say, I'm going to conclude in favor of my alternative hypothesis, there is a 0.2858 chance that I just made a type 1 error, that really the null hypothesis was true, and what I'm saying is false. So by choosing HA, there would be a 28.58% chance of committing a type 1 error. So what do? We compare the p-value against our level of significance. And since 0.2858 is greater than my level of significance, which was 0.05, we instead choose to conclude in favor of the null hypothesis. Because there's just not enough evidence. In other words, if my sample had more than 27 quitters in it, then I would calculate a smaller p-value. And if it was small enough, it would be less than alpha, and then I could conclude in favor of my alternative hypothesis. And that's the sense in which my level of significance tells me how much evidence I need. Alternatively, maybe I could keep exactly the same sample fraction, but if I just had a larger sample size, that's another way of reducing your p-value, is just by increasing your sample size. Because a larger sample size represents more evidence for your alternative hypothesis. So let me go ahead and pass this out. This is kind of important.
What if the p-value is the same as, what was it?
The exact same.
Yeah, what if it was the exact same?
So technically, the probability of that happening is 0, because it's a continuous random variable, and so we don't even think about that or worry about that. Yeah, it's a good question. The packet you're about to get has 6 pages. This is going to help you out a lot, I hope, when you're doing the homework and when you're getting ready for the test. This is a summary of everything I said about hypothesis testing in general on the first page, every conceptual thing. On the second page, this is a summary of how to perform a hypothesis test about one fraction. What we just did on the board here is a hypothesis test about one fraction. If you flip it over, you'll see the instructions for how to perform a hypothesis test for 2 fractions. That hypothesis test would be like, I want to compare 2 different fractions and see if one's larger than the other. On the next page, where there's a 3 at the top, the third hypothesis test you need is a hypothesis test about one mean. We're not talking about that today. We're going to save that for a couple weeks from now. And then we will talk about hypothesis tests for 2 means when we're trying to compare 2 means. And then the last type of hypothesis test is comparing 2 means in a matched pairs experiment design. So I know this is a whole lot of stuff, and I didn't want you to have the burden of writing this down in your notes while I lecture. So at least you have a typed out notes packet you can reference later when you do your homework, when you study for your test.
Hypothetically, could we take this entire pamphlet to the test?
No. So on your test, you can't use this. You can't take this with you on your test. But as you prepare for the test and you make that 8.5 by 11 front and back sided page of handwritten notes, like figure out what in here can you not memorize, and then write that on your handwritten page of notes. For example, the test statistics are really hard to remember. I would, if I were you guys, I would be copying the test statistics formulas into my notes, because some of those get kind of hairy. If you look at the hypothesis test about 2 fractions, like the test statistic has that big ugly formula. I would write that one down in your notes so you can have it on the test. But below that, before you look at the test statistic, or I should say after, everything is pretty much the same for every hypothesis test after you have the test statistic. For fractions, you're going to pull up a standard normal distribution, and you're going to find the area on Desmos like that. And for means, we won't use a standard normal distribution, we'll use another probability distribution. But again, you'll be using Desmos, and it's pretty similar as a process. Okay, we started at 12:15. Oh wow, we still have 30 minutes. Cool. I thought this was going to take a lot longer. We still have lots of time. So just to remind you, the value P0 that defines the null hypothesis, the difference between the null and the alternative, that's the threshold value. So we suppose that the true underlying population fraction is equal to the threshold value. We know that it's probably not, but we like to pretend that the actual population fraction is the threshold value. We know if the variance is greater than 10, then a binomial distribution can be modeled using a normal distribution. And if my population fraction is equal to the threshold value, then this is the formula for the population standard deviation. A z-score for my sample fraction would be the sample fraction minus the population fraction, the mean of that distribution, divided by the standard deviation of the sample fraction. And then the reason there's two formulas here is I'm just replacing this sigma with the formula for sigma. So these are equivalent, but that's what we use to calculate. That's called our test statistic. And there's actually two cases. We just talked about the case where, and I think it might be backwards in this packet, I just didn't fix it on my notes. Yeah, okay. I fixed the packet, I didn't fix my lecture notes. Let me fix my lecture notes really quick. I want to make sure that my directions of my inequalities match yours. Let me do these, because in your handout, I wanted the left to be on the left side of the page and the right to be on the right side of the page. So if your alternative hypothesis is like in the example we just had, where we are hoping to find evidence to show that the population fraction is greater than some threshold value, then what we do is we set the p-value equal to the probability that x is greater than our test statistic, and we find that using Desmos by using right and area. The p-value is the probability we make a type 1 error. We want the p-value to be small. If there is any evidence at all in favor of the alternative hypothesis, then our p-value must be less than half. So here's another way that you should think about this, another way you can check your work on a test, is like, if you know you have some evidence in favor of your alternative hypothesis, and you calculate a p-value that's like 0.5, sorry, or 0.6 or 0.7, right, something larger than 5, then something's wrong. That should clue you out that, you either calculated the p-value wrong, or maybe there isn't evidence. You got to go back and check your work. If I were to take 1 minus my p-value and multiply that by 100%, that's what we call the percent confidence that we have in our alternative hypothesis. So like in the example we just worked, oh, I think I closed it out of it. We had a p-value of like 25-ish, like 0.28, right? And so a p-value of 0.28 would mean I have about 72% confidence in my alternative hypothesis. And 72% confidence is not very high, right? I don't know. It's something, but it's not great. But I think it's cool that we can put a percent confidence down numerically without having to like give it your gut feeling. And if there is any evidence at all in favor of your alternative hypothesis, then we have at least 50% confidence in the alternative. Okay, let me fix the direction of my inequalities here so I don't forget to do it later. And then I will export this as a PDF again. And we'll work one more example in our time together. Oops. Okay, so what if we want to test a hypothesis about the difference between two population fractions? Usually we make a statement like this. In a drug effectiveness trial, we want to find evidence for the claim, users given the new drug experienced fewer symptoms than those who were given placebo. So let P1 be the fraction of drug users experiencing symptoms. And let P2 be the fraction of placebo group members experiencing symptoms. And if our drug is more effective than placebo, then we expect P1 to be less than P2. That's what we're trying to find evidence for, so that's our alternative hypothesis. And this is what I mean about the difference between two population fractions. Like, one population is the group that's going to be using this medication, and the other population is the group that's not using the medication, and we want to compare the two, see what the difference is. In a hypothesis test, we always presume that the null hypothesis is true at the threshold value. So in the case of a hypothesis test about two fractions, we're assuming that they're actually equal to each other. And if these two population fractions were actually equal to each other, then the best approximation of that same population fraction is called the pooled sample fraction. And the way you calculate the pooled sample fraction is you add the number of patients experiencing symptoms from both groups divided by the total number of participants from both groups. Pool the two groups together. And we're going to call that p hat without a little subscript. Just like before, we can calculate a p-value using the standard normal distribution, but this time the test statistic is bigger and nastier. This is our test statistic for comparing two population fractions. And this is something that I would write down on your notes page. So that way on a test, when you get this kind of hypothesis test, you can say, oh yeah, I have that test statistic. I can calculate that really quickly, and then I can pull out my standard normal distribution and get this p-value super fast. So let me show you an example. The fraction of Nasonex users who experience headaches as a side effect is greater than the fraction of non-users. That's the claim. A clinical trial involved a designed experiment of 3,774 people. 2,103 subjects were placed in the experimental group and were administered a 200 microgram dose of Nasonex. The remaining 1,671 subjects were placed in the control group and were administered a placebo. 547 subjects in the experimental group reported headaches. 368 subjects in the control group reported headaches. Is there enough evidence to conclude that our claim is true at a 95% level of confidence? So I'm going to have to decide which group is the population number 1 and which group is population number 2. And it doesn't matter how you choose to do this. You'll get the same conclusion either way. But let's go ahead and say group number 1 is Nasonex, and group number 2 is placebo. So whenever I want to state my alternative hypothesis, I'm just trying to put this claim into symbols. And I think the symbols I want to choose are that P1 is greater than or less than P2. It's going to be greater than. It's because P1 is going to be the fraction of Nasonex users, and P2 is going to be the fraction of placebo users. And that's the claim I'm trying to find evidence for. The null hypothesis is just the converse of this. So you say it's less than or equal to.
But if you were trying to, because the claim is like not in support of Nasonex, but if you had a claim that was trying to like see if Nasonex was safer or like more effective, you would do it the other way.
Yeah. So there's kind of like 2 types of clinical drug trials. There's like safety trials and there's effectiveness trials. And before the FDA approves your drug, they want to show that it's both safe and effective, right? They want to show that, like, yes, it's going to do what it claims it's going to do. In the case of Nasonex, it's like reduce allergies. And then B, that it's not going to cause severe side effects that are going to make the patient worse than they are to begin with, right? Like, make sure it doesn't cause your liver to shut down. Because I'd rather have allergies than a broken liver. So this is an example of a safety trial, right? And you're right, it is backwards from effectiveness. If the purpose of Nasonex was to reduce headaches, then this would be a less than claim. But since the headaches are a side effect of taking the Nasonex, now it's a greater than question. That's a good point. Okay, so we've got our alternative, we've got our null hypotheses. The level of significance is what? Yep. I'm going to write alpha equals 0.05 for my level of significance. Is there any evidence at all in favor of the alternative hypothesis? Well, I don't know. I think we ought to do some calculating first. Like, what is P1 hat? That would be x1 over n1, which is going to be of the Nasonex group. 547 divided by 2,103. And P2 hat is going to be the number of headaches in group 2 divided by the sample size of group 2, which is 368 divided by 1,671. Okay, would you say there's any evidence at all that Nasonex causes headaches? Yeah, since P1 hat is greater than P2 hat, yes, there's at least some. We don't know if there's enough evidence yet, but we know there's some evidence. And so we expect our p-value to be less than half. And we expect our confidence to be greater than 50%. We just don't know if it's above 95%.
So if you get to that question and there's no evidence at all in favor of the alternative.
Yep.
Do you just stop there and say, am I proven in favor of the null hypothesis?
Yes. Yeah, you would just stop and you'd say, yep, there's no evidence whatsoever. We can just stop and conclude that the null hypothesis must be true. Or I guess like in technical terms, you'd say we cannot reject the null hypothesis. We don't have enough evidence in favor of the alternative. But as long as there's some, we can keep moving forward and we can say, let's calculate the test statistic. And the test statistic is that big, ugly formula right here. It's P1 hat minus P2 hat divided by, and we also have to calculate that pooled fraction. And that shows up there in the test statistic. It's also on your printed handout. So let's do the pooled fraction next. So I'm going to have 547 plus 368 divided by 2103 plus 1671. My pooled fraction is 0.2424. And then whenever I go to do my test statistic, I say my formula is P1 hat minus P2 hat divided by the square root of P hat times 1 minus P hat times the square root of 1 over n1 plus 1 over n2.
So instead of doing the x1 plus x2 over the p1 plus p2, could you just do p hat 1 p hat plus p hat 2 over 2? Because that kind of comes out to the same number.
You could do that only if you had exactly the same sample sizes. Like if n1 were equal to n2, that would work. But it won't be exactly correct if you have different sizes of samples. Yeah, good question. Okay, so here goes. Here's my big test statistic. I'm going to name it Z0 in Desmos. And then we'll have the P1 hat 0.2601 minus the P2 hat 0.2202 divided by the square root of that pooled fraction, which is 0.2424 times 1 minus 0.2424, and then we multiply that by another square root of 1 divided by, the N1 sample size is 2103, plus 1 divided by the N2 sample size, 1671. And so my test statistic is 2.841. 2.841.
Can you go back on what you just calculated?
Mm-hmm. Oh. And now that we have our test statistic, the next step in Desmos is to make a standard normal distribution. And by the way, I've said this before in class, but if you didn't want to retype out the 0.2424 every time, you could also just type in the letter P, because with the first line, Desmos knows what P is. So I could also do that if I wanted to. It still gives me about the same answer, doesn't it? 241. Yeah, it would still be 2841 when I rounded 4 sig figs.
How did you get the Z0 in there? Did you just type?
Yeah, you just type in the letter Z and the number 0, and it happens. All right, so here's my standard normal, and what we're supposed to do is figure out the right area, and I want the probability that x is greater than 2.841. And it's hard to see because here's 2.84, but it's this little shaded region here. That shaded region, which is only a very small part of my normal distribution. Most of it's unshaded, but if we just zoom in right here, then we can kind of see where it is. And so it's a small number because it's a small shaded area. And that number is my p-value. It's 0.002249. Cool. All right, any questions about how we found this in Desmos? You guys know how to do normal distribution, right area, and so on. If it was the opposite alternative hypothesis where I wanted to know P1 less than P2, then I would choose left area. And for that reason, it doesn't matter whether you make the Nasonex group 1 and the placebo group 2, or you make the placebo group 1 and the Nasonex group 2. The process works exactly the same, and you calculate the test statistic exactly the same. But if you switch the order of these numbers, you'll get the same but negative 2.84 for the test statistic. And then you would have to choose left area for the negative 2.84, but you'll get the same number. You get the same p-value. Okay, so back to our problem. We got the test statistic. We got the p-value. How do we interpret this p-value? Well, for one thing, remember the p-value is the probability that if we were to conclude in favor of our alternative hypothesis, that we'd be making a type 1 error. So if I say that Nasonex causes headaches, there is a 0.002249 probability that I'm making a type 1 error, that I'm wrong, that I'm false, what I'm saying is false. The other thing is this happens to be less than my level of significance, right? My level of significance was 0.05. And since the p-value is less than the level of significance, then we choose to conclude in favor of my alternative hypothesis, which says Nasonex causes headaches. And then the last thing you might say about the p-value is that if I took 1 minus the p-value, and I multiply that by 100%, I'll do it in Desmos. 1 minus the p-value. Then I would have a 99.7751 % confidence in my alternative hypothesis. So this is a significant amount of evidence that Nasonex has headaches as a side effect.
I have a
You can be pretty
question.
sure about it. Yeah.
How did we find 0.5 for the level of significance? Is that just a standard? Or is that just because it was 95?
Exactly. You got it. It's because we had a 95% level of confidence. And the level of confidence is 1 minus the level of significance. Or I could also say, sorry, the level of significance is 1 minus the level of confidence. That goes both ways. Because they are complements of each other.